This video presents our KAI 2020 publication, Touché, Data-Driven Interactive Sword Fighting in Virtual Reality, developed within the Center for Digital Entertainment at the University of Bath in cooperation with the Video Games Studio Ninja Theory. But before going into that, I want to take a moment to look at some examples of sword fighting in video games. How does sword fighting look in a screen-based game? This video is from a relatively recent video game, and it showcases all sorts of interesting sword fighting behaviors, including attacks, blocks, counterattacks, and so on. Let's compare it with one of the few examples of VR sword fighting games. We can clearly see that all of those interesting behaviors are not there anymore. The opponent character just seems to stand there repeating the same attack, not actually reacting to the actions of the player. The question is, why does VR look worse? On the one hand, there is the matter of control. Unlike traditional games, where the press of a button clearly signals an action, in VR, the control inputs are just hand positions in space, and it becomes harder to interpret the intentions of the user. On the other hand, the animation of the character necessarily becomes more complex, since it has to react to the player input. What we will want is a way to work at a higher level of abstraction. So on the control side, instead of dealing with this spatial user input, we will want to have concrete gestures, such as attack. Similarly, on the animation side, instead of thinking in terms of skeletal configuration of a character, we will rather have simple expressions of behavior, like block. The advantage is that, at this level, it becomes much easier to reason about what the character should be doing. The question, of course, is how do we go from here to there? This is where our data-driven interaction framework comes in. This diagram provides a high-level overview of the system. In the first place, we have the spatial input coming from the user. In order to transform this input into specific gestures, we train a data-driven model capable of recognizing these gestures. Knowing the gesture that the user is performing, a designer can come up with a behavior planner that determines what the character should be doing depending on that gesture, that is, the desired expression. A data-driven animation synthesis model is then responsible for translating this expression into a specific animation for the virtual character, in turn realizing the interaction between the two parties. Let's now go into the gesture recognition part in a bit more detail. The first thing we need to define is what we understand as gestures in this context. For us, a gesture is a directional strike from the player, classified as one of 8 possible directions. The problem of gesture recognition is then, given the position of head and hands of the player, what is the gesture that is currently being performed, and how far into the gesture we are, which is something that we will need later. We chose a neural network to solve this problem. However, we need gesture data to be able to train a neural network. We designed a data collection environment in VR, where the user is asked to perform specific gestures. This gives us good quality label data. Furthermore, we augment this data, applying small random perturbations to its speed, trajectory, or scale. We use a hierarchical convolutional network that allows the gesture recognizer to use information from many recent frames of data while keeping a low complexity in the model. This figure shows the results of training our model on about 11 minutes of data. The horizontal axis represents the progress of the gesture, from beginning to end. The green line shows that, although the classifications around the boundaries of the gesture is less clear, the core section is very well recognized. Similarly, the light blue line, representing the progress precision, which should be close to the correct dark blue line, provides a sufficiently accurate prediction for the middle region of the gesture, allowing us to tell whether we are roughly at the beginning or end of a gesture. That was gesture recognition, so let's now go into the behavioral planning stage. The goal of this stage is to have a designer decide what is the expression that the character should adopt, given the incoming gestures from the player. This can be expressed as a very simple state machine like this. The character starts by walking towards the player, and then comes into a defensive state where it tries to block incoming strikes. From here, it can either proactively start an attack after some time, or if the player has completed a strike, it may attempt to counterattack. While performing the attack, the character may detect that the player is starting a strike, and decide to stop its own attack in an attempt to block it. It may also happen that the player actually hits the character, in which case the attack is interrupted. Otherwise, the attack will be successfully completed, and in all cases, the character will come back to defending. There are some parameters to this behavior. First, we can choose how frequently the character will start a proactive attack. Second, we can choose the probability that the character will counterattack the player. And finally, we can also choose the probability that the character will abort an attack to defend itself. After behavior planning, the last piece of our framework comes in, animation synthesis. There are two different kinds of animation that we need to produce, attacking and defending. The attacks are fundamentally easier to animate, since they are proactive actions with clearly defined boundaries. So we can simply use fixed motion clips to animate offensive actions. The defense, on the other hand, is reactive in nature and must adapt to the player actions. So we use a data-driven animation model to synthesize it. The problem is then the following. Given the current pose of the character and the position of the source, what is the next defensive pose? As before, we use a neural network to solve this problem. We collected around 15 minutes of sword fighting motion capture data, containing the pose of the character skeleton and the position of both swords. We extract relevant features of this data, such as joint positions and velocities, or the recent trajectories of the swords. We use a particular grid model architecture for our neural network, represented in this figure. Here, each dot in the 3D grid represents a whole neural network model. We compute a weighted mixture of all these neural networks according to their proximity to the player's sword tip. This gives us a single mixed neural network that is used to predict the next pose. In order to evaluate the quality of this model, we calculate the error between the correct position of each pawn and the predicted position, measuring the area of the skew quadrilateral method defined by them. This histogram shows that the aggregated error is usually around 0.25 square meters and rarely over 0.50 square meters. These are relatively small errors considering the proportions of a human body. As expected, the bone driving the sword position is the top source of error, followed by the wrists. This is not necessarily an issue though, as slightly different sword positions can be acceptable as long as the body pose is plausible. This completes the whole picture of our framework. Hopefully you are now hyped to see what it actually looks like, so let's take a look at the video recording. As you can see, the character alternates attacks and blocks as expected, and it is able to follow the player's sword while it is defending. Overall, the animation looks smooth and reactive to the actions of the player. We ran 2 user studies to learn what were the impressions of users about our systems. We designed 3 evaluation conditions: an aggressive and an skill condition, with high attack rate and incapable of counterattacking or performing a quick defense, a defensive and skill condition, with a lower attack rate but capable of counterattacking and performing a quick defense, and a control condition, which did not use our system, but instead replayed a mixture of fixed offensive and defensive animation clips. In our first study, we asked participants to watch a video of each of the conditions in action and answer some questions about each of them. These questions included the intrinsic motivation inventory enjoyment questionnaire, questions from the realism scale from the immersion questionnaire, and Likert scales for different adjectives describing the videos. Our results show that the control condition was consistently perceived as less realistic and more repetitive, while the defensive and skill condition showed the best performance overall. For our second study, we asked participants to play against each of these conditions and asked them the same questions as before, plus questions from the presence questionnaire. The results confirm our findings from our first study, showing that our system is perceived as significantly better in terms of realism, interests, or repetitiveness. I want to finalize this presentation with some final thoughts about the lessons we learned from this work. We found that the combination of models and methods from different areas, such as gesture recognition and animation synthesis in this case, opens the door to new designs and experiences that surpass the combined potential of each of the individual elements. We also noted that the alliance of data-driven methodologies with human experience and guidance really brings in the best of both worlds, and we feel is the right path towards the design of smarter and more empowering tools and methods for creators. In that respect, our partnership with Ninja Theory proved fundamental to our success, providing invaluable feedback that really informed our decisions trying to build a system that could actually be used by industrial practitioners. We found the evaluation of our system to be particularly challenging, not being directly comparable to prior work, but the combination of both technical and user evaluation provided us with a more comprehensive assessment of the quality of our work. We believe, however, that this will be an area of growing interest in the following years, as both academic and industrial researchers become more aware of the possibilities of incorporation of data-driven techniques, not only to interaction, but to digital content creation in general. Our work is a step forward in this direction, and a hint to the new workflows and methodologies that will shape the interactive experiences of the future. Thank you.